Hello, y'all. Welcome to lesson 100 of my DP chemistry curriculum. Today we're going over reactivity 3.1.9 and 10. This is an HL topic. We're going to talk about the pOH scale, which describes the concentration of OH of a solution. pOH is equal to the negative log base 10 of the hydroxide concentration, or hydroxide concentration is equal to 10 to the negative pOH. And so we should be able to interconvert H plus, OH minus, pH, and pOH values. All right. The reactivity for 3.1.10 is the strengths of weak acids and bases that are described by their Ka, Kb, pKa, or pKb values. And we should be able to interpret relative strength of acids and bases from this data. So these are the two topics we're covering today. They're both short in their own respect. Starting with pOH, the power of hydroxide. This is pretty much an exact derivation of pH, where we get pOH is equal to the negative log base 10 of the concentration of OH minus. We can also invert that to get the concentration of our hydroxide ions is equal to 10 to the minus pOH. So it's the exact same thing as hydronium or hydrogen ion concentration and pH. This, of course, because it's hydroxide, is a measure of how basic something is, or alkaline something is, and that is pretty much all there is for pOH. What we can do, though, now that we understand it, is bring in our ionic product of water. And we know that Kw is equal to the concentration of H plus in a solution times the concentration of OH minus in a solution. And we know that that's equal to 1.0 times 10 to the minus 14th. Taking the respective pH and pOH values, we can therefore transform this in understanding our pH scale. We know that the pH plus the pOH of a solution will always equal 14. So this can give us our scale. So our pH and pOH are just relative amounts compared to 14. So a pH of 1 has a pOH of 13. So we can interconvert between all of these quite easily using the ionic product of water along with our pH and pOH equations. So that's all there is for 3.1.9, which is why we also bring in 3.1.10, which is where we're going to talk about acid and base dissociation constants. Now, those constants are going to be Ka and Kb, Ka for an acid, Kb for a base. Now, what we know about the dissociation of strong and weak acids, or at least strong acids and bases, is they fully dissociate. If we look at a strong acid, maybe HA, so this is strong. If right now HA is our strong, we know it will dissociate into H plus plus A minus, or if we're doing a water equation, it'll be H3O plus, and that's if we're adding water into this. Then we get that separate equation. But we know they fully dissociate. I use a regular arrow for any chemical reaction to represent that. The thing is, when we have a weak acid or base, then we get a partial dissociation. So if we're looking at some generic weak acid, so let's look at a generic weak acid. We'll represent that now. Once again, I'm using HA, but this time it is for the weak acid. We can see the equation of HA, aqueous, plus water, liquid, reacts in equilibrium. So we have a forward and reverse reaction to form hydronium ions, aqueous, plus our anion, our conjugate base, aqueous. So in reaction, we have this equilibrium, which means we, of course, can represent it with the equilibrium constant. But when we're talking about acids and their dissociation, we actually change Kc to be Ka, which is our acid dissociation constant, which, of course, is a measure of hydronium ions multiplied by the anion divided by the concentration of our original weak acid, HA. This is a heterogeneous solution, meaning that it has states of matter of aqueous and liquid throughout. And so we're, of course, ignoring the liquid in our equilibrium equation. Once again, this Ka is specifically our acid dissociation constant. Now, using equilibrium, we can actually figure out a couple things. First off, we can determine that this is temperature dependent, much like the equilibrium constant. And there will be a uh, fixed value at any given temperature. So generally our temperature is 298 for this, but we'll have some given fixed value of Ka for each individual acid. Furthermore, we know that a weaker acid will dissociate less, and therefore we will have less of this top product, meaning that it will have a lower Ka value. So now we can measure strengths of weak acids relative to one another. So if we have an example here, let's look at three acids, acid and Ka. And our three acids that we'll use throughout this are methanoic acid, ethanoic acid, and propanoic acid. We don't have OChem yet, but the only difference between each of these is meth means one carbon, eth means two carbon, prop means three carbons. Ethanoic acid is the common one that we generally use, CH3COOH. So we have methanoic, ethanoic, and propanoic acids. Their relative Ka values are 1.8 times 10 to the negative fourth. We have 1.8 times 10 to the negative fifth, and 1.4 times 10 to the negative fifth. Looking at these values, I can identify that propanoic is the weakest because it has the smallest value for Ka, its acid dissociation constant. Therefore, I can also find that methanoic is the strongest of the three. It is not a strong acid, just out of these three weak acids, it is stronger than the other two. We can now expand this example. So let's say given a generic weak base. So in this example, our weak base will be B. Our base, aqueous, can react with water to produce. Oops, and that is the wrong arrow. We're talking about weak acids and bases. We'll use our equilibrium arrow to produce BH plus aqueous plus hydroxide aqueous. Once again, we can look for our equilibrium constant, but now that we have a base, that is Kb, our base dissociation constant, which is going to be equal to the concentration of BH plus times hydroxide divided by our original concentration of base. And there we can easily find our base dissociation constant. It's the same equation and followed by this. So let's just label that as base dissociation constant. And following the same logic we did for our acid dissociation constant, we can generalize that a weaker base would have less dissociation and therefore a lower Kb value. So we can follow the exact same logic we did if we compare three generic bases. So let's do base and our Kb values. We can look at ammonia. We can look at methylamine and ethylamine. Again, we're following the same trend. Ammonia has Ammonia has no carbons. It's just NH3. Methylamine has one carbon, CH3, NH2. Ethylamine has C2. Actually, I'll write out the structural formula. CH3, CH2, whoops, NH2. So we're just adding a carbon, much like we did with our acids. And our Kb values for this are 1.8 times 10 to the minus fifth. So it's kind of the same K value as our ethanoic acid. 4.6 times 10 to the minus fourth, and 4.5 times 10 to the minus fourth. Looking at these three, I can now tell right off the bat that ammonia is going to be our weakest base. It has the lowest Kb value, with methylamine having the highest. So this is going to be our strongest here, just beating out ethylamine. So we can use Kb values to determine the relative basicness or alkalinity or acidicness of different solutions. Now, the last part we did is we use concentrations of H plus to get the pH, OH minus to get the POH. Now we're going to figure out something called pKa and pKb. These values are just made to easier represent the dissociation constants. So pKa has the equation, the negative log base 10 of Ka. pKb has the equation negative log base 10 of Kb. You'll notice they're exactly the same as the equations for pH and pOH. We're now just using the dissociation constants. So these are going to give us values within the range, values within uh, larger numbers. So we're going to get numbers like on our pH scale, generally around anywhere from 1 to 14 or 0 to 14. So we can calculate these all. And what we'll find out is much like if we have a very acidic thing, very acidic has a high concentration of H plus and therefore a low pH. So basically what this means is that the higher the value we plug in, the lower our P value will be. So we can see this when we do an example. And what I'm actually going to do is take our bases back. So I'm going to cheat here for my notes. But if I look at my bases and I create a new column called pKb, what I will find is that my Kb for ammonia is 4.75. My Kb for methylamine is 3.34 and 3.35 for ethylamine. For these values, I noticed that the stronger the value, the lower the pKb. We can actually repeat this if we pull our acid values too. So I'm going to cheat once more, grab these acid values, bring them all the way down, and make my new column, pKa. With my pKa's, I will find that I have a 3.75 pKa for methanoic, a 4.76 and 4.87 for the other two values. I'm going to just bring these over so we can compare. Oops. And yet I am still missing my values. One more time, charm. We'll just intercept the middle of the page. So as I look at my values, the things that are stronger, stronger have a lower pKb. And again, the stronger value has a lower pKa. So it's a little weird, but what you need to generally just keep in mind is that a lower pKa or pKb is equal to a higher Ka Kb, which is equal to a stronger acid or base. So the last part I'm generally going to keep out and just, well, last part I'm just going to put in as one final just summation of all of it once more is if we look at Ka, Kb, pKa, pKb, and finally pH, because we'll kind of always bring it back to pH. It's if we have a very high Ka, we'll have a low pKa, and we'll have a high pH. If we have a high Kb, we'll have a low pKb, and we'll have a low pH. Oops, and look at that, I've already made a mistake. Inverse these two. Low pH, high pH. So this is what I mean by it gets a little confusing. Something that is very acidic will have a low pH. Something that is very basic will have a high pH. So they kind of get inversed, and it's a lot of terms that you want to try and keep straight. As you see, I just made the mistake there. So this is something you want to be careful about as you're going through your DP exam. Please keep that in mind as you go through and have a great day.